Welcome to Lesson 2. Last time we met the nucleus, the forces that hold it together, and the photon. Today we go a step stranger. Antimatter. How particles are destroyed and created out of pure energy. And Feynman diagrams. The little maps that show you how particles actually talk to each other. Here's the plan for today. We begin with annihilation and pair production. Every particle has a matching antiparticle, same mass, opposite charge. When a particle meets its antiparticle, they obliterate each other completely. All of their mass is converted into energy, carried away as photons, following Einstein's famous equation E equals mc squared. Now here's a detail examiners love. You always get 2 photons out, not 1. But why do we get 2? The answer is momentum. Before the collision, the total momentum is essentially 0, so afterwards it must still be 0, and a single photon flying off in one way couldn't balance that. 2 photons in opposite directions can. And this isn't just abstract. Annihilation is exactly the physics behind a PET scan in a hospital. Pair production is simply annihilation run in reverse. A single photon, if it carries enough energy, can spontaneously transform into a particle and its antiparticle, energy becoming mass rather than mass becoming energy. The key condition is the enough energy part. The photon must carry at least the combined rest mass energy of the 2 particles it's creating. Any less and it simply can't happen. You can't make a bit of a particle. If there's spare energy beyond that minimum, it goes into the kinetic energy of the pair. Both of the processes we've just mentioned are just energy and mass swapping places, and the tool for the calculation is E equals mc squared. Give it a mass, you get the energy locked inside it. Give it an energy, you get the mass it could create. We can see that we only get a small amount of mass from a large amount of energy because the speed of light c is such a large number. One practical thing you must be comfortable with is units. In particle physics, we usually measure energies in electron volts, usually mega electron volts, MeV. But to put numbers into E equals mc squared, you need joules. So learn this conversion. 1 electron volt equals 1.6 times 10 to the minus 19 joules. Mega electron volts being 1.6 times 10 to the minus 13 joules. In a typical question, you usually work out a photon energy from annihilation, or check whether a single photon is energetic enough to produce a particular pair. Now on to Feynman diagrams. Here's the big conceptual leap. Particles don't actually touch each other to interact. Instead, they exchange something, a so-called exchange particle or virtual particle, and that exchange is what we experience as force. It carries momentum, charge and energy between the 2 particles. Feynman diagrams are how we draw these interactions, and there are 2 rules to get right every time. First, time runs up the page and space runs across. Second, the lines are not the literal paths the particle take through space. They just show what goes in and what comes out. The wavy line in the middle is the exchange particle representing the force. For the weak force, those exchange particles are the W and Z bosons. Let's look at some standard examples you might be asked to draw in an exam. The simplest is 2 protons repelling each other. They interact by exchanging a virtual photon. Virtual because it's there doing its job, but you can never detect it directly. In fact, if you tried to observe it, the interaction wouldn't happen at all. Next is electron capture, where a proton and an electron interact with each other, cancelling out the charges and producing a neutron and a neutrino. This is one of the weak force interactions, and the others include beta minus decay, beta plus decay, proton antineutrino interaction, and a neutron-neutrino interaction. These all use a W boson as the exchange particle. The golden rule for every one of these diagrams is that everything must balance before and after the interaction. Charge in equals charge out, and so on. The decays look a bit different because they start with 1 particle instead of 2 coming together, but the balancing rule still holds. A final important note on the W boson. It comes in two versions, W plus and W minus, and that's because the two beta decays go in opposite directions. Beta plus turns a proton into a neutron, and beta minus turns a neutron into a proton. Both are weak force processes, but unlike the photon, the W boson has a non-zero rest mass, so it's a proper massive particle. Its range is absolutely tiny, around 1,000th of a femtometer, which is why the weak force acts over such minuscule distances. We've made it to the end of the video. Make sure you really understand the Feynman diagrams, as they can be tricky under exam pressure. Thanks for watching, and check out my tutoring page in the description.